Hello everyone. I am a student at Peking University. The paper I will be presenting today is titled Actionlet-Dependent Contrastive Learning for Unsupervised Skeleton-Based Action Recognition. Previous skeleton-based contrastive learning transforms the skeleton data for creating positive and negative samples through data augmentations. However, existing contrastive learning methods treat different regions of the skeleton sequences uniformly, disregarding the fact that motion regions contain richer action information. This approach may degrade motion-correlated information too much. Additionally, global average pooling used in feature extraction can introduce non-motion information, reducing feature separability. To address these issues, we propose a novel actionlet-dependent contrastive learning method. By utilizing actionlets, we design motion-adaptive data transformations and semantic-aware feature pooling to separate action and non-action regions. In the era of big data, images and videos have become crucial for human information exchange. The internet and surveillance cameras now contain vast amounts of video data, including human actions. Automatic video action analytics has practical applications in various fields. It aids in monitoring dangerous or violent actions in surveillance videos, improves retrieval efficiency by annotating actions in video retrieval, enables human-computer interaction by recognizing actions, and assists in home surveillance by detecting actions like falling. Skeleton data, specifically 3D skeletons, plays a vital role in human action analytics. It represents the three-dimensional coordinates of human joints, making it simple to capture human movements. Skeleton data is more robust to illumination and background clutter compared to RGB data. Its low dimensionality enables real-time online processing. However, skeleton data has limitations, such as the loss of visual information and noise due to occlusion or inaccurate collection. Traditional fully supervised skeleton-based action recognition requires extensive labeled training data, which can be tedious and expensive to annotate. To address this, self-supervised learning utilizes automatically generated supervision with pretext tasks to learn feature representations from skeleton data more efficiently. The limitations of previous contrastive learning approaches, which treated different regions uniformly, have prompted us to propose a novel actionlet-dependent contrastive learning method. By incorporating actionlets, we address the suboptimality of applying data transformations to all regions, which can degrade motion-correlated information. Our approach utilizes motion-adaptive data transformations and semantic-aware feature pooling to separate action and non-action regions. This allows the model to focus on capturing motion information while reducing interference from static regions during feature extraction. Additionally, the similarity mining loss further regularizes the feature space. Experimental results demonstrate that our method achieves remarkable performance and validates the effectiveness of our designs. During the process of obtaining sequences without any action occurrence, we have observed that most action sequences have no action in the majority of regions. Instead, motion tends to occur in small localized areas, such as the hand or head. Exploiting this observation, we can easily obtain a static anchor by averaging all the actions in the dataset. This average represents a relatively static sequence, as most regions have no motion. To determine the regions where motion takes place, we input the skeleton sequence with the average motion into the offline encoder to extract dense features. We then calculate the cosine similarity between these features and the dense features of the original sequence. By back-propagating and reversing the gradient of this similarity, we can identify the region where the similarity can be reduced. These gradients are globally average pooled over the temporal and joint dimensions, resulting in neuron importance weights called alpha. The importance weights alpha reflect the magnitude of each channel dimension's effect on the final difference. Consequently, these weights serve as a difference activation mapping. We perform a weighted combination of the difference activation mapping and the dense features. The linear combination allows us to select features that negatively influence the similarity. The actionlet region corresponds to areas where the generated actionlet's value exceeds a certain threshold, while the non-actionlet region represents the remaining part. Figures provide a visualization of the actionlet, with yellow joints representing the actionlet. Our actionlet is spatio-temporal because the joints with motion may change during the performance of an action. Building upon the actionlet concept, we have developed a motion-adaptive transformation strategy. This strategy involves applying the proposed semantically preserving data transformations specifically to the non-actionlet regions, while keeping the actionlet region unchanged. By reducing interference in the motion regions and focusing on stronger transformations in non-actionlet regions, our motion-adaptive transformation strategy enhances the model's ability to learn semantic consistency and achieve stronger generalization performance. In addition, we employ a semantic-aware feature pooling method to further improve the representation of motion. By extracting features solely from the actionlet region, we ensure that the features are more representative of the motion itself, without being influenced by the semantics present in static regions. The pipeline of our actionlet-dependent contrastive learning approach involves several steps. In the unsupervised actionlet selection phase, we leverage the difference from the average motion to identify the region of motion. For contrastive learning, we utilize two streams: the online stream, updated by gradients, and the offline stream, updated by momentum. We augment the data by applying Motion Adaptive Data Transformation, MATS, using the obtained actionlet on the input data. In offline feature extraction, we employ semantic-aware feature pooling, SAFP, to obtain an accurate feature anchor. Finally, by utilizing similarity mining, we increase the similarity between positive samples and decrease the similarity between negative samples. This comprehensive approach allows us to effectively leverage the actionlet-dependent contrastive learning framework, resulting in enhanced feature representation and improved performance in various action recognition tasks. In order to evaluate the effectiveness of our approach, we conducted experiments using a multitask self-supervised learning framework. We trained action classifiers under various configurations, including unsupervised, semi-supervised, and supervised learning settings. Through comprehensive and rigorous experiments conducted on 3 datasets, we demonstrated the remarkable performance of our method in action recognition tasks. Our approach consistently outperformed the baseline methods, showcasing the superiority of our actionlet-dependent contrastive learning framework. The results of our experiments indicate that our model is a powerful feature extractor capable of learning more discriminative and general features for skeleton-based action recognition. We are grateful to all who have listened to our presentation, and we believe that our research contributes to advancing the field of self-supervised learning and its application to skeleton-based action recognition. Thank you.